There you go. We're going to look at Avogadro's law. So I know this is going to be shocking. Avogadro's law comes from the work of a guy named Emilio Avogadro. I know, that's shocking, isn't it? Yeah, exactly. All right, so Emilio Avogadro came up with Avogadro's law, and it proves that equal volumes, he proves equal volumes of gases have equal number of moles, and thus particles. So that is to say, if I have 1 mole of any gas, it will have the same volume as any other gas has moles. Okay, now with that said, we don't use it that way. What we do is we use it to connect moles and volume, so I can look at how a volume changes and find the number of moles, or look at how moles changes and find the number of volumes. So like we did last time, we're going to do a little graphing here. I'm trying to organize my screen over here before I walk away so it can be easily seen. It's just not wanting to be cooperative. Okay, we're going to just have to go with that. Okay. It is what it is. Okay, let's do a little graphing like we did last time to see the relationship. I have a graph here, and I'm going to put, if I had a pen, there we go. I'm going to put volume over there, and my volume will be in liters according to the data table. And I'm going to put moles down here. The abbreviation for moles is little n, lowercase n. And that's going to be, of course, measured in moles. And let's say I need to go from 1 to 2.4. Now, we did that last time, so I remember we could go by 0.2s. So we're going to go with 1, 1.2, 1.4, 1.6, 1.8, 2.0, 2.2. 2.4 is enough for us. We could keep going if we wanted to. I don't have to start at 0, 0, so I'm not starting at 0, 0. It'd be like starting at 0.8. So be it. Now the moles I need to get from 5 to 12. Let's see if I can just count this out by ones. 5, 6, 7, 8, 9, 10, 11, 12. Yep, that would fit. So we're just going to go by ones down here. 5, 6, 7, 8, 9, 10, 11, 12. I could stop there. I think I'll just go to 13 and call it good. There we go. So when laying out a graph, it's always good to just take a moment and count your spaces and make sure what you think is going to work before you write anything down. And I have 1 and 5. So put a big dot there. I like big dots so I can see them even after I draw the line. 1.2 and 6. So that's convenient. Worked out quite well. How about 1.4 and 7? Yep. So we got really lucky with the way this graph lays out. It looks like it's hitting all of these vertices here. I am double checking as I do my dots, but it worked out quite well for us. See, now the great thing about seeing this graph is I could even predict what would it be with 2.6. I don't even need that data anymore. I can use the line of the graph. This would be where it would be great to grab your ID, use it as a straight edge, and connect all those dots with a nice straight line. I'm going to try to, it's not going to go well, but I'm going to try to use freehand a perfectly, wow, told you it wasn't going to go well. Perfectly straight line through all these dots. It's supposed to be straight, That's probably as good as I'm going to get free-handed. Might be the best artwork I've ever had, which is kind of sad, I know, but that's the way it is. Okay. I hope you might remember the graph from last time. The graph from last time kind of curved downwards. This one is a very different graph. Doesn't it look different? That's going to tell us a very different relationship. So tell me this. As moles increases, as I go from left to right along the bottom axis here, what's happening to the volume? Is it going up or down? The line's going up, isn't it? So that means the volume's going to go up as moles goes up. Now, did you catch what I just said? As moles go up, the volume goes up. So guess what? If moles went down, the volume would go down. When they both go the same direction like that, it's called a direct relationship. They are directly related. So last time we had an inverse relationship. One went up, the other went down. Today, it's a direct relationship. And that's what this graph's going to show us. So now we can keep that in mind as we work. When one goes up, the other is going to go up. Anyone need more time with the graph portion here? Okay. Let's do some examples. My examples are not going to be as fun as last time. I do apologize for that. But we're going to do some examples. I'm going to start with, probably not get ahead of myself. I'm going to start with just blowing up a balloon. So we're going to call it a balloon of air. And I'm going to try to drag this over so it's easier for the online students to see. Here's my little window of what's going on in the room. Okay, I have a balloon. I'm going to put it on the scale here and zero out the scale. So now the balloon has no weight on the scale. And I'm going to put some air into it. And I totally forgot to grab a clip. There they go. I had the balloons ready, but not the balloon clips. I'm just going to clip it closed, so it's not going to. I'm apparently going to break the clip with a balloon. I literally just broke my clothespin with a balloon. Like, I don't know. It literally, like, exploded. Anyone wants a blue busted clip, you're welcome to it. Okay, I'm going to have to try again. Okay. Here comes an orange one. Hopefully the orange one doesn't break. Yay. Okay. So there on my balance, I have a balloon. We can see it online in the little corner there in the room. You can clearly see I have a balloon. We're going to just draw this. Now this is, for me, going to be kind of a smaller balloon. So we're going to draw it like that. And I'm going to read the mass right off the balance. That's why I like having it on the balance. The mass is 2.3 grams. Okay. Now this next thing I need moles. Now, what is in the balloon is the air that I exhale. Most of the air that you breathe in and exhale is nitrogen. Like, as much as you think you breathe in oxygen, you breathe in some oxygen, your body uses that oxygen, but it's like mostly nitrogen. It really is a good thing. If it was pure oxygen in the atmosphere, you could never put out any fire. So the very first caveman to ever light a fire would have burnt the entire planet down and we wouldn't exist. So, I know, isn't that a lovely thought? Okay, I have to let someone in to Zoom real fast. Hold on. Okay. Anyway, it is mostly nitrogen. Nitrogen has a molar mass because it's N2 of 28 grams per mole. So I'm going to put 28 grams there, 1 mole there. And since you all in the classroom have calculators, I'm going to ask you for this number, 2.3 divided by 28. How many moles are we going to get? I'm expecting around like a 0.1 something. 0.1? Really? Just dead on?
That's a 0.002.
Oh, it's even less than. Okay, let's go with, hold on. My guess was off, 0.082. Okay, let's just call it that, 0.082 moles. Okay. Now, I also did not want to bore you with too much math here. So I have a ruler. I am measuring the diameter of my balloon. And in my super fancy, really old calculator, don't ask how old it is, it's what I used for my high school career, I have the equation for the volume. So right now, this balloon is holding 1,767 milliliters of air. 1,767 milliliters of air. Okay. I know that seemed like a lot of setup, but bear with me here because I'm going to make a change. So I got my little window back so online students can see. I am unclipping the balloon and I'm going to really, really inflate it now. And hopefully I can get this to stay on the balance. I know I might need someone's help over here going on. Okay, there we go. I'm breathing on it. 2.49 grams. Now look at how much bigger it got, and it didn't get much, like not much more mass is in there. Well, okay, gases don't carry much mass. They do carry some mass, but not a lot. Now we need moles again, so I'm going to ask you to do the same calculation we just did of this time 2.49 divided by 28. Oh, and I forgot my picture. I'm sorry, I skipped ahead. There's my big balloon. Probably makes it look a lot bigger than it really is. Okay, if someone would do 2.49 divided by 28. Maybe like 0.09 something. I'm just kind of guessing at this point in time. Sorry? 0.09. Is there any number after the 9? 8? Okay, we'll go with that, 0.098. So the moles have definitely gone up. If the moles goes up, what do we expect to happen to the volume? We hope it goes up too. So I'm going to take my ruler. I'm going to measure that diameter. It is definitely bigger now. I'm going to put it into my fancy schmancy calculator. And I now have 8,181 milliliters. 8,181. So 8181. I can't find my pen. Oh, there it is. Okay, 8181 milliliters. So did our volume go up? Yeah. And that's great because that's literally what we expected from that. Okay. So there is my first example. If anyone wants a big pink balloon at the end of class, you're welcome to it. Don't get into trouble with it. Okay, I know. Yeah, I know. I'm talking to you. Don't get into trouble with it. Okay. Next up, I'm going to make a water balloon. I am hoping I'm going to make a water balloon. Wow, school water pressure is so impressive. Okay, that's good. Okay, I'm going to use the same clip that I know doesn't break apart here. So now I have a water balloon that I'm hoping will stay on my balance. Come on. There we go. Yeah, I might actually want like a guardian of the balloon or something. There, no, yeah, if someone doesn't mind just holding a finger on the top lightly to just keep it from rolling. Appreciate it. Thank you. Okay. First off, this for us is going to be the big balloon. So in your, okay, so up here we're going to have water balloon. Big balloon. What's our mass say?
It says error 2.
Oh no. I put so much water in it, the balance can't even handle it. Okay, let's try getting rid of a little water here.
Yep.
I did not think this balance would be so picky.
Error 2.
I'm sure it's your fault, right?
No. There is. Oh, there is a button.
No, I
At this point,
literally.
it might be better just to put it in a little beaker.
Well, but I know, but then I can't show you the volume change. Okay, we've just barely made it where the balance is okay. We're going to go at 333 grams. Yeah, okay, 300. If you already wrote 333, that's fine. She's right, it rounds up to 334. I'll put 334. Okay, so again, I'm going to want the moles. So we're going to take 334 grams, and my balloon, I zeroed out. So it's just the water inside. Water is 18 grams for 1 mole. So if someone would take 334 and divide by 18, let me know how many moles we have. 18.5 repeating, so let's call that 18.6 moles. Okay, and I can still do the volume of the balloon calculation. Okay. Sadly, it's not going to be as big a number as I was going for, but it is what it is. 382 milliliters is in that balloon. Okay. So I'm wanting to, just a moment here, I'm putting that back on. I'm going to click to my Zoom window. There's a little picture of my sad little water balloon because my balance can't do more than that. There we go. Now I'm actually going to do something I already did. I'm going to let even more water out of the balloon. That's going to be my next one. Okay, so I saved just a little bit of water in my balloon here. What has happened to the volume of the balloon visibly? I let water out so it's smaller, right? So let's see how this all works out numeric wise. 122 grams. So I'm going to take 122 grams. 18 grams is 1 mole. How many moles is this? I would guesstimate about 6 something. 6.7. Okay, let's call it 6.8. I'm good with that. Let's call that good. Okay, so the moles have gone down. Now, what did we visibly see with the balloon? We visibly saw it get smaller. So if volume goes down, the mole should go. Oh, that's kind of sad. If the volume goes down, the mole should go down as well. Okay. So while I calculate, I'm going to put the new little picture of the balloon up there so online students can see. There's my new little itty bitty tiny balloon. The volume is now 113 milliliters. So yes, our volume went down as our moles went down. And our volume went up as our moles went up. Or the other way around, the moles went up as the volume went up, and the moles went down as the volume goes down. They're directly related, so up is up and down is down today. Anyone need more time with my little pictures here? A little bit longer? Okay, I'm still seeing some people finishing their writing. I'll pause a moment. I know for next time I need to get a different balance, one that can take a much larger water balloon. Someone needing to be reconnected in Zoom. There we go. Okay, if you're not done writing down these examples, I can come back at the end and give you a chance to write them down. Let's look at the equation. Notice how it looks different than last time. If you remember, I know it was 2 days ago. Last time it was multiplication. What math is going on now this time with one being on top and one being on bottom? It's going to be division this time. So that's because it is a direct relationship. That's why this formula looks this way. Last time's inverse relationship looked different. We have moles before, we have volume before, we have moles after, we have volume after, and I gave you some reminders, ways to clearly figure out what number means what. Moles would be in moles, volume could be in milliliters or liters. Now there's one catch with volume, and I'm not going to do this to you, wouldn't trick you like this, but it is important that if you start with milliliters, that you end with milliliters. Or if you start with liters, you end with liters. Whatever the volumes, whichever label it is, should be identical. And I'm not going to do that in the practice or on the test and mix them up or anything, but I just want you to be aware of that. You would want to be careful if you're not working on an assignment for my class that the liters matches liters or the milliliters matches milliliters. Okay, so on the back of your paper, we've got 4 examples we're going to go through, and then we'll get into Canvas and do some practice there in Canvas. I'm going to do the same thing I did last time, and as I read, I'm going to circle my numbers with their labels. So that's going to help me know what is what. A person inflates a balloon with all the air in their lungs, which on average is 6 liters, and they end up putting 0.25 moles of air into the balloon. The person then adds a second full amount of air from their lungs into the balloon. So now there's a total of 12 liters in the balloon. How many moles of air is now in the balloon? So let's make our little chart. And what would liters be a good label for? Volume, right? L liters would be a great one for volume. So let's call that V1. And then I see a moles. Well, moles should be moles. I don't know how else to explain that to you. Would abbreviate moles as MOL. You don't have to abbreviate it, I won't care. And now I'm told we have a 12 liters. What would liters again be good for measuring? A volume, right? So that's my V2. So clearly I'm looking for N2 with this problem. So here's our equation, N1V1 equals N2V2. Now, I'm going to ask a question just because I'm old. How were you taught to handle this equation? Were you taught cross multiply divide? I'm just curious. Because I've watched my children come home and talk about butterflies.
Oh, butterfly method, the fixed cross multiplication.
That exactly, yeah. And I'm like, no, that's cross multiply divide. They're like, no, it's a butterfly, Daddy. You don't know anything. I'm like, okay.
Butterfly
fine.
is literally just the fun.
And then have you heard bat and ball? I know, right? Okay, that's how it, okay. I was taught cross multiply divide. It is cross multiply divide. It is. But if you would like a different version of the equation, you could mathematically rewrite the equation to look like that and do the same math we're about to do. Now notice it has a 1 and a 2 on each side. But I offer that to you. You could use this perfectly instead of that equation. They are substitutes for each other, whichever one you prefer to use. Okay. And again, you get open notes tests. So if you want to write that second version on these notes, then you know it's here for test time, and you can even decide test time which way you want to go. I'm going to cross multiply divide. Hope you're all good with that. 0.25 moles gets divided by 6.0 liters. And that's going to be equal to my X, 12.0 liters. So I'm going to cross multiply 0.250 moles times 12 liters, and then have 6 liters times my X, and so I'll divide by 6 liters, and I am totally good to go here. What do we get for X? 0.5. Okay, now I see 2 digits, 2 digits, 2 digits. Give me something after the 5. Oh, just a flat out? Okay, so 0.50. The round to our significant digits there. And then notice liters cancels liters. They have to match. So moles is my label. Now let's look at what happened. The volume went from 6 to 12, so the volume went up. And my moles went from 0.25 to 0.5. So my moles went up. So it's good. It went in the same direction. By the way, here's the bat and ball. My son was taught, here's your baseball bat, and you cross multiply, and then you divide by the baseball. So, and I'm like, why can't we just call it cross multiply divide? But it is what it is.
Butterfly method is the oldest one, I think, other than the original cross multiply.
Yeah, my daughter, who's older, was telling me about butterfly well before my son and his teacher in baseball, and I don't know if
The
it was.
baseball one sounds a little more. Right, this sounds complicated.
I know, I'm like, what's wrong with cross multiply divide, huh? Okay. Unless there's any other questions though, let's move on to example 2. 3 pumps with a hand pump inflates the beach ball to 8 liters with 0.350 moles of air in it. To fully inflate the beach ball, it needs to have 1.20 moles of air. What's the fully inflated volume? So I'm going to make my little chart here. Oh, no, I wanted to here. And liters is great for volume, and moles is great for moles. And I have another mole, so that must be my N2. So what am I looking for this time clearly? I'm looking for V2. So N1V1 equals N2V2, 0.350 moles divided by 8 liters equals 100, or no, 1.20 moles divided by X. Now, does it weird you out that X is in the denominator? I hope not, because it doesn't change anything. It's still cross multiply divide. Still going to be 8 liters times 1.20 moles will equal 0.350 X, moles X. So I'm going to divide by 0.35. And there we go. So still cross multiply divide, doesn't matter if your X is in the numerator or denominator, the math still works out just fine. Notice moles cancel, so liters would be my answer. So if someone would take 8 times 1.2 and divide by 0.35 and give me 3 digits, because I've got 3 digits, 3 digits, and 3 digits. Okay. Hold on, point what?
4.
Okay, start all over then, I missed it.
27.4.
27.4. Okay, thank you very much. That does sound reasonable. 27.4 liters is what I'm being told. My moles went up from 0.35 to 1.2, so I'm hoping my volume went up. Oh yeah, it went from 8 to 27.4. Moles goes up, volume goes up. It works well. See a few people still finishing up this one, so I'm pausing a moment. Okay, anyone need more time with this example? Okay, let's look at number 3 then. Before being slashed, a car tire has a volume of 10 liters. Afterwards, the volume becomes 2.3 liters and only contains 0.5025 moles of air. What was the original amount of moles in the car tire? Well, if I'm looking for the original amount of moles, that would be N1. So already I feel like I'm looking for N1. But let's make the rest of our list. I see a liters, so I'm going to put 10 liters as V1. That was the original size of the car tire. I have a new size of the car tire as 2.300 liters. And my new mole, 0.5025 moles, there we go. All right, so N1 V1 equals N2 V2. X is my N1, 10.00 liters is my V1. 0.5025 moles is my N2, and 2.300 liters is my V2. Notice since I have liters and liters, I know the liters is going to cancel, and that's how I'm going to get moles as my label. I see 4 digits on every number, so give me 4 digits once you got an answer.
Do you want it rounded?
Give me 4, so round at the very end of the 4th.
2.185.
Sounds pretty good to me. Could that work with others who have it calculated? Yeah, okay. We're going to go with that. My X, my N1, was 2.18 moles. Notice what happened. The volume went down. I mean, that's what's happening if your tires get slashed, that they're going to deflate. And so my moles went, this is my original here that we just found, my moles also went down, so it does work. When the volume went down, the moles went down. Now remember, I solved for N1, so you have to start at 2.185 and go to 0.5025 to be sure you see how it goes down. I'll pause a moment, let people who are still writing this example catch up. We'll move on to the next one. So many of you are working ahead, which I love, that's great. We'll try to just hop into the next one and fly through. Okay. 90,000 moles, 15,000 moles, And 30,000 liters. Ooh, this one's gonna be scary. Okay, is it really gonna be scary? Okay, 90,000 moles is what I start with, so it's only gonna be scary if you're scared of big numbers. It's really no big deal there. I'm told afterwards it becomes 15,000. And afterwards it has 30,000 liters. So there's my chart. V1 is my x. So N1 V1 equals N2 V2. 90,000 moles over x, 15,000 moles over 30,000 liters. Okay. Now it is cross multiply divide again. Before I even do the math, notice what I can tell. Moles is going to cancel. I'll have liters as the label on my answer. And tell me, to go from 90,000 to 15,000, what happened to the moles? Did they go up or down? They went down. So I expect my x is going to be bigger than 300,000 because as this happens, if we said the moles went down, we should see the volume go down. So I hope my answer is larger than 300,000. Okay, so cross multiply divide 90,000 times 300,000. There's a lot of zeros to count. That's the scary part. 90,000 times 300,000 divide by 15,000. What do we get? If you just want to read off the zeros, I'm good with that.
1,800,000.
Okay,
I don't know.
fair enough. I was told 1,800,000. That actually seems good to me. Is that okay with others who've calculated it? Okay. Label is liters, and there we go. So as long as you can keep the number of zeros on each number okay as you type it into your calculator, we'll be there. All right, so that is how Avogadro's law works. It's a direct relationship. If one goes up, the other goes up. If one goes down, the other goes down. There is an 8-question practice in Canvas. So let's use the rest of this time to go into Canvas and practice. I am here to help you as you do that practice. I think considering you all know cross multiply divide, you're probably not going to need any help, but don't hesitate to ask. If you need scratch paper for writing on as you do these, please feel free to come up and grab some from me if you want, or use your own, I don't care. Let me pass out Chromebooks, but please let's get into Canvas, get this taken care of in the next 45 minutes, and then you're good to go without any homework.